right, let's talk about the combined gas law. Emphasis on the word combined. So what is the combined gas law? We've seen 3 gas laws so far, and in all of them we've had 2 variables with the third one constant. So we've got volume, temperature, and pressure. And let's say we hold volume constant, we get the relationship between pressure and temperature, and as they affect each other. That one's Gay-Lussac's law. If the temperature is constant and doesn't play a role, the pressure and the volume change, and that's Boyle's law. And if we say the pressure is constant, we can get the temperature and volume relationship, which is Charles' law. So those are the 3 gas laws we have. And if we add those all up, pressure, volume, and temperature, they all change at the same time. What do? We use the combined gas law, combine all 3. And it's going to be very similar math-wise to what we've already done in the 3 prior gas laws. We're using ratios to solve problems. Let's take a look. A helium-filled balloon has a volume of 50 liters at 25 degrees Celsius and 1.08 atmospheres. Okay, so all those numbers go together. I have an initial volume, V1, of 50 liters, my initial temperature, and my initial pressure. What volume, there's my question, so what is the final volume going to be, the second volume, if I have a new pressure and a new temperature? All right, let's pull all those numbers out. Initially, I have a temperature, it's a 1, of 25 degrees Celsius, which is, add 273, and we get 298 Kelvin. My initial volume, 50 liters, and my initial pressure is 1.08 atmospheres. What's going to happen if the temperature 10 degrees Celsius, which is really 283 Kelvin, what's going to happen to the volume? I don't know. And the pressure as 0.855. Okay, now I've got 3 variables to start with, initial and 3 in the final. So what's going to happen as these conditions change? So I want to see what's going to happen to my volume. 50 liters is what I'm starting out with. And we're going to use the ratios just like we did before. First one, let's look at the temperature ratio. What exactly happened to the temperature? 298 to 283. The temperature went down. And because the temperature went down, the volume and temperature are directly related, the volume needs to go down too. So 298 and 283, if I put the smaller number on top, the temperature, the volume will go down because this number is less than 1. And then in a completely separate ratio, let's look at what happens to the pressure. The pressure went down too. So if the pressure goes down, what happens to the volume? Well, if pressure went from 1.08 to 0.85, that means the volume is going to go up because they are opposite. So for this ratio, because the volume is going up, I need to put the bigger number on top. And I just do each ratio separate. Just like we're doing 2 separate problems, except we're kind of combining them with the combined gas law. Units cancel out, and I multiply my volume by this ratio and by this ratio, and I get 59.97 liters, or with significant figures, round that up, 60.0 liters. All right? So 2 ratios now with the combined gas law instead of 1. All right. There's also the term here that we've used, we've already defined it once, but let's look at it again, called STP. And the world agreed to a standard temperature and pressure in order to compare one gas to another. And you can see the variables in the word, STP. There's a temperature term and a pressure term. Okay, standard temperature and pressure. The temperature term is 0 degrees Celsius or 273 Kelvin. The pressure term is 1 atmosphere or its equivalent. So if I wanted millimeters of mercury, standard pressure is 760 millimeters of mercury, because those are equal. So we can convert those as well. When you see this term, STP, you need to remember that these are the conditions under STP. Those numbers will not be given. You need to know what STP is and use those values. So let's take a look at an example where we're trying to see what something will do at STP. If we have 350 cubic centimeters, what is that? Cubic centimeters. Well, that is a volume term. Cubic centimeters. So that's a volume. You need to recognize that. It's helium gas. The temperature of that gas is 22 degrees Celsius, and the pressure 99.3 kilopascals. Okay, let's pull all that information out. My volume initially, in an initial set of conditions, is 350 cubic centimeters. Temperature 22 degrees Celsius plus 273 equals 295 Kelvin, and my pressure 99.3 kPa. What is kPa? Kilopascals. That is one of our pressure units. What volume would this gas occupy at STP? So I want to know what my new volume is going to be. So there aren't any more numbers in the problem. How do I know my final temperature and pressure? It's right there. The numbers are given. TP, temperature and pressure. What is standard temperature? 273 Kelvin. Standard pressure, 1 atmosphere. Or, because I'm in kilopascals, the units have to match. I know that 1 atmosphere is also equal to 101.325 kilopascals. Okay? Standard pressure. It's just in a different unit. Now we can say what's going to happen to the volume. Well, if I have 350 cubic centimeters, let's take it ratio by ratio. How is the temperature going to affect it? How's the pressure going to affect it? The temperature, 295 to 273. It looks like it's going down. Therefore, the volume also needs to go down. So I need the smaller temperature on top, 273 Kelvin over 295 Kelvin. That number is less than 1. That is a ratio. That'll make the number smaller. So my volume goes down. Good. Separately, let's handle the pressure. Pressure goes 99 kilopascals to 101. Pressure went up from the start to finish. The volume, opposite of pressure, is going to go down. So the smaller one needs to be on top again. 99.3 kilopascals, 101.325 kilopascals. Kilopascals are gone, and I have two ratios, and I can figure out just how much my volume is going to go down. 350 times this ratio, and when it goes to STP, the final volume is going to be 317 cubic centimeters, because the units are over there, cubic centimeters. 3 significant figures in my answer. I'm okay. And that is the combined gas law. There's 2 examples there. Make sure you catch the STP when that comes up, and we're just doing 2 separate ratios together instead of 1 with the other 3 gas laws.